Hello, and welcome to lesson 4 of this introduction to calculus with Wolfram U. The topic for today's lesson is the limit of a function, and it is today that we begin formally the study of calculus in this course. So, the limits are a central topic in any calculus course. So let's begin with an overview of the topic. So, here are two simple plots. I'm going to plot x from -1 to 1. That's, of course, just a straight line. And then I'm going to plot x squared over x in the same limits. And I again get back what looks like essentially same straight line. On the other hand, if you look at the function x squared over x, then strictly speaking, it's not defined when x is 0 because you're doing 0 over 0. And that becomes clearer if you define a function g with that expression. So g over here is defined to be x squared over x. And if you try and find the value of g at 0, then you get back the value indeterminate. The quiet over here only says that I would not like to see any warnings that Wolfram Language would give us in this case. Okay, so the point is you have two very similar functions, but the second one has a slight issue at 0. Now, even though it is not defined at 0, we would certainly like to know what the behavior of the function is near this point. And that's what limits are all about. They are about tracking the behavior of a function near a point. So the mathematical way of doing this is called a limit. So here's an example to show the notion of a limit. Let's take f of x equal x squared minus x plus 2. Again, you want to find the behavior of this function as x approaches a certain value. So let's say you want to focus on the value x equal to 1 and you make a table over here. Now, don't worry too much about how to make the table. That's not too important for us. But as you take values close to 1, so you begin from 0 and go up to 1, very close to 1, but not 1 itself, you see the values get close to 2. And just the same thing happens on the right, that the values are very close to 2 when you're close to 1. So it appears that this function gets closer and closer to 2 as the values of x grow closer and closer to 1 from both the sides. So one would then say that the limit of this function when x approaches 1 is 2. So limits are just a way of showing the behavior of a function near a point, but not necessarily at that point. Okay, so some examples. Let's begin with a function which is a trigonometric function divided by a simple polynomial. So it's a trigonometric rational function, and you want to find the limit of this function as x approaches 0. So if you look over here at the table, it's clear that as you approach 0 from either side, the values approach 1. And in fact, if you plot the function, you get the same kind of guess that the value of the limit seems to be 1. So the table says 1, the plot says 1, but in practice, it's best to use the limit function in Wolfram Language, which tells you the limit is actually 1. So tables are good, plots are better, but limit is the best. And limit will always tell you exactly what the limit of a function is at a point. So the whole theme of our discussion will be to try and move towards using limit whenever you can. As my second example, let's take a rational function. That's a rational function. It's a polynomial divided by a polynomial. Now notice that when x is either plus or minus 1, there's a problem with the denominator becoming 0. So let's say you want to talk about the behavior near -1. So near -1, it looks like the values are very close to -0.5. Let's plot the function. And it does look like when you're close to -1, the values are close to -0.5. So it looks like the function approaches -1/2 as an exact number as x approaches -1, and you can confirm that with limit and get back that value as the actual limit. Okay, so as my next example, let's consider this piecewise function g of x. Now the piecewise part over here is rather simple. it's just negative 0.75 at x equal to negative 1, and then it's the same rational function as before everywhere else. Now, if you make a table of values, it's clear that as long as you stay away from negative 1, then there's no problem at all, and the values approach negative 0.5 as before. So here's a plot which shows that there is a problem at just a single point, negative 1, but everywhere else, things are just the same as before. So in fact, the limit does seem to be negative 0.5. So let's confirm that over here, and you do get back negative 0.5 for this piecewise function limit. So now let's go on to a slightly more complicated example, namely an algebraic function. So here's an algebraic function. It's got a square root in it, and the denominator is x squared. So when x is 0, that's a problem. But fortunately, everything is removable in the sense that there really is no problem at 0. In fact, if we make a table of values, you see that when you're very close to 0, the value is very close to 0.25. So you plot the function, and you see that the value at 0 does seem to approach 0.25. And you can confirm the answer with limit, and you get back the value 0.25 as an exact number, a quarter. Okay, so let's go on now to a slightly more tricky function. So here is a trigonometric function. Now, if you make a table of values over here, what you'll see is that the values all seem to be 1, mostly. So it looks like there's a problem because the limit seems to be 1, but the intuition tells you that things might be more complicated. So let's plot. And when you do that, you see the behavior is much more wiggly. It's much more complicated. So what you need to take away from this is that tables are useful, but they are not terribly reliable. So the plot says that this limit probably does not exist. But in fact, you can confirm the answer with limit and check that the answer is actually indeterminate. Indeterminate says that this limit does not exist. Okay, so let's move on now to a slightly more complicated function, and I hope you realize by now that we do need some different ways of finding limits. But just for now, let's take the same approach and make a table of values over here. When you make a table of values and you're close to 0, you see that the values seem to approach 0.015 on either side. So as an exact number, you would expect the limit to be around 3/200. You plot the function. The limit does look like 0.015 at 0. And you can confirm the answer with limit and get back the correct result, which is 3/200. So that's the value of the limit function. It will tell you exactly what the limit is at a point. Okay, so having talked about limits, it's convenient sometimes to talk about one-side limits. So here's an example where you have a piecewise function. Now if you plot it, you see that when you approach the point 0 from the left, the answer is -1. When you approach it from the right, the limit seems to be 1. So the question is, how do you check that with the limit function? Well, we have an option called direction. So when you say direction from below, you're going from the left. When you say direction from above, you're going from the right. And when you do that, you see that you get back the values -1 and 1 respectively. And of course, because you don't have the same behavior on the left and right, you get back indeterminate as the answer for the limit. So one-side limits are really quite useful because they let you analyze more and more complicated functions. So here is a piecewise function. It's got several pieces. Notice that when you plot the function, then there are 3 values of interest to us. There's 1, there's 4, and there's 6. Now, 4 is no problem at all. It's nice over there. At 1, it's almost okay, except that you have a slight piece outside of a point over here given by this piecewise component. At 6, you have a slightly more difficult problem because you actually have a jump. So it would look like when you approach 1, the value must be 3 for the limit. That's 3 over here. When you approach 4, the answer must be 6. That looks clear as well. Now, when you approach 6 itself, the limit does not seem to exist. And you can confirm this by using the limit function. Now, this strange thing over here is what we call a map function, which actually lets you find the values of the limits at different points in one stroke. And you can confirm that at 6, you actually have separate limits on right and left by doing the direction computation, and you get back different answers. So surely the limit does not exist at x equal to 6. Okay, so now we need to turn in a slightly different direction and talk about infinite limits. So here's an example where you have a rational function, and what you want to do is to use a table of values that's given to you to try and guess what the limit might be at the point x equal to -1. So here's the table, and what you see is that whether you approach -1 on the left or right, the values seem to blow up. They become infinite, but they become negatively infinite on one side and positively infinite on the other side. So you can confirm that with the limit function. You see the values become -infinity on one side and infinity on the other, and you can check that the limit does not exist finally. So now we are talking about infinite limits, and that leads us to the concept of an asymptote. So what's an asymptote? It's a point in the graph where things become infinite. So here's an example. You got 1 over x minus 1 the whole square as a function, and whether you approach it at 1 from the left or right, the values become infinitely large in a positive sense, and you can confirm that with a plot to check that the limit is actually going to be infinity on either side. Well, if it's infinity on either side, then it is infinity, so the limit says, yes, the limit is infinity at 1. So that's what we call a vertical asymptote. It's a kind of vertical line that shows you the function is becoming infinite on both the sides in this case. But you could also have a slightly different behavior. So here's f of x equal to 1 over x, and if you plot it between -1 and 1, then at 0, you have a different behavior on the left and the right. So on the right, it approaches plus infinity. On the left, it approaches -infinity, and you can confirm that with limit. So you see the limit does not exist, and what you have is a vertical asymptote of a slightly different kind. Okay, so the question is, how do you find asymptotes in general? Well, that's really a hard problem, but let's say if I give you the cotangent function, and I said, find the asymptotes between -2 pi and 2 pi, what you could do is to make a plot of the function. And the plot seems to say that there are problems at 0, you can see over here, and then at pi, and then at 2 pi, etc. So let's look at 0, and you see that the function values are -infinity and infinity from the two sides, so you certainly have a vertical asymptote at 0, and just the same thing happens at all the other multiples of pi. So you can see a limit does not exist at any of those points. So given a function, you could try to plot it and then use limit to figure out where the asymptotes might be. Okay, so finally, I have an example in which you actually do need to use tables. So here's an example in which you have two variables. You've got an h and an x. Now, the problem is that because x is not known to you, you cannot graph the function. So graphing will get you nowhere in this case. But what you could do is to make a table of values, and then what you see is, well, roughly speaking, if you expand it out, you get x squared plus 2xh plus h squared minus x squared. So if you do a bit of algebra, it'll be clear to you that what's going to get left over is just 2x. Right, so the point over here is, the limit over here is just going to be 2x. Okay, so we've seen now that tables are quite useful in some cases, but in general, you should try and avoid them. So that brings me to the end of today's lesson. And what you've learned is that the limits are a good way of figuring out what happens as a function approaches a certain value of x. Now, the function doesn't even need to be defined at the point at which you want to find a limit, but as long as the right-hand limit and the left-hand limit both exist, you are fine. So for a limit to exist, you must have the right-hand limit and the left-hand limit to be equal. They could both be infinite, but they must both be equal. And as you saw in the last example, tables are really useful in some cases, but in general, you want to avoid using them, and you really want to use the limit function. So in the next lesson, we'll talk about the laws of limits, which actually let you do limit computations very efficiently without using tables. But before you do that, I recommend that you go over today's lesson and carefully master all the details from notebook, look at the exercises, and make sure you understand the notion of a limit really well before we actually start computing them at a really fast pace. So that's all I have to say for today's lesson on the limit of function. I hope you enjoyed it. I hope that you really benefit from this first introduction to calculus with limits, and I'll see you next time. Thank you.